Hello and welcome to this video about diffraction. We're going to look at what diffraction is, what factors affect the amount of diffraction, something called Huygens Principle, and diffraction gratings. Diffraction is simply the spreading of waves into a region behind an obstruction. You've probably all seen what looks like the bending of a wave around an object. If we have wave fronts that are approaching right here, traveling in this direction, and we have an obstruction right here, diffraction makes it appear as though these waves bend around like this on the other side. That's kind of what's going on right here. You can see the waves are traveling in this direction, and we get what looks like a bending of these waves around this obstruction. Here we see it again. The waves are, the wave fronts are coming in at this direction, and they're hitting these two obstructions here, and you can see diffraction. They are bending around, or what they appear to be bending around those objects. We can think about diffraction and interference. What if we have diffraction occurring through two slits? We obviously get this bending of these wave fronts around those openings because there are obstructions here. So we get interference on the other side. This is just a picture showing the crests. In the dark lines are where the crests would be. The troughs would be these lighter black lines. You can see that constructive interference is occurring right here and right here and right here because you have places where the crests are interfering here and creating constructive interference. Here the troughs are interfering together. Crests are interfering, troughs, crests, and troughs. These are in phase. Here, this is not constructive interference. This would be destructive interference because you have the trough crossing the crest, and a trough crossing with a crest, and a trough interfering with a crest. So here are the portions of destructive interference, whereas here would be the portions of constructive interference. So the amount of diffraction will depend on two things: the size of the obstacle or the opening, but it will also depend on the wavelength, and it will depend on how the two are related. Here we can see an example of a pretty wide gap, but we have a pretty small wavelength. Here, if we narrow the gap with that same amount of wavelength, we get more diffraction. So the narrower the gap, the more diffraction you will see. But also, the distance, the wavelength here, the distance between those wavefronts is going to matter. If we increase the wavelength, we will also see more diffraction. Here's just another illustration of that with a large opening compared to the wavelength. We don't see any diffraction, but then when we make that opening smaller compared to that wavelength, we will see the diffraction. Here, this idea about the width of the opening and the amount of diffraction that's occurring is illustrated in this picture. We have, here is a width of 0.16 millimeters. We're narrowing that width and making it smaller and smaller, and you can see that there's more diffraction. It's a greater amount of diffraction. We're getting larger patterns on the screen. In a diffraction pattern, the central maximum is going to be twice as wide as the secondary maxima. And here's another little naming nuance here. We call this the central maximum in a diffraction grating. And then we just call all of these secondary maxima. And this central maximum is going to be twice as wide as these secondary maxima. This brings us to something called Huygens Principle. And it simply states that each portion of a slit acts as a source of waves. So let's think about light and diffraction in relation to light and light waves. And we think about this slit, and light is being passed through this slit, the very small slit. There are little portions of this slit that are acting as independent sources of light, single different sources of light. And light from one portion of the slit can interfere with light from another portion of the slit. This is how we get a diffraction pattern for light passing through a single slit. We call each of these waves a Huygens wavelet, and at our viewing screen, very far away down that direction, at the very midpoint, all the rays from that slit are traveling the same distance, and we see a very bright fringe appearing. This is a representation of how destructive interference can be occurring. And when we look at the wave, the little wavelet here from source 1 versus the wavelet from source 3, you can see that they are exactly half of a wavelength difference. So they are perfectly out of phase with one another. And so the interference between those two is going to end up producing the first dark fringe. For angles other than those at which destructive interference completely occurs, which at this angle we get complete destructive interference right here, but for other angles, some of the light waves remain uncanceled and don't cancel each other out, and at those angles the light will appear on the screen as part of a bright band. So this idea has been incorporated into a device that is constructed called a diffraction grating. And diffraction gratings are made to either transmit or reflect light, and based on this idea that waves will be traveling different path lengths before they reach the screen is going to end up producing this diffraction pattern because the diffracted beams are going to end up interfering with each other and make this pattern on a screen. Diffraction gratings can disperse polychromatic light into its component colors, much like a prism. The condition for bright line formation at angle theta is given by the equation for constructive interference. So we can just use what we've been familiar with, the distance between the two slits or two of the slits times the sine of theta. The angle theta is going to give us m times the wavelength. Here is just a picture of polychromatic light being dispersed by a diffraction grating, and you can see the pattern that is formed. I just labeled 0th order would be where m equals 0. Here would be the first order. M would be -1 on this side, +1 on this side. Here are the second orders. And notice that the angle of deviation for the first order maxima, the angle is smaller for the blue light than for the red light here, and then the red light would be here. You can see, if you think about this in terms of this picture, and here's our light source, and it's passing through this diffraction grating, you can see that the blue light, the angle to get for this blue light being dispersed is a smaller angle than what the angle would be for the red light, and that has to do with the fact that they have different wavelengths. Let's do a sample problem together. Let's say we have a monochromatic light source and it's shining at the surface of a diffraction grating with 5.0 times 10 to the third lines per centimeter. The first order maximum is observed at a 15-degree angle. Find the wavelength. In order to do this problem, I need to let you know something, that the number of lines per unit length in a grating is the inverse of the line of separation, or D is what we've been calling that. That means D equals 1 over whatever the lines per centimeter or lines per whatever unit length are. We can find D in this way because this is the relationship there. When we go ahead and take 1 divided by 5 times 10 to the third, we get 2.0 times 10 to the -4th centimeters, because we've just done this in centimeters. If we are going to use our equation, we need to change this into meters. There are 100 centimeters in a meter, so we get 2.0 times 10 to the -6th meters. We also know theta is 15 degrees for the first order maximum. And for the first order maximum, m is going to equal 1. Now we can use our equation and plug the values into this to solve for the wavelength. Here I've plugged all of our values in to our equation, and I solve for my wavelength, 5.2 times 10 to the negative 7th, and it's going to be in meters. Oftentimes, we write things in nanometers because this is such a tiny number. And remember that a nanometer is equal to 10 to the negative 9th meters. And so we can rewrite this as 5.2 times 10 squared nanometers if we like. Either one is correct. Here are a few advanced ideas. Resolving power is the ability of an optical instrument to separate two images that are close together. How does resolution depend on wavelength and aperture width? And to give you a little hint, you can look at page 611 in your textbook and research some of that. Or try the conceptual challenges on page 607 in your textbook. Or maybe you have some other ideas, questions, or things to look into. Look forward to seeing what you come up with, and we'll see you in class.